Hey, welcome back. In the last episode, we implemented Monte Carlo tree search. We didn't quite manage to get it working because of some bugs. I fixed all of them and managed to get it working. Partly it was, I think we stopped. I think we already fixed the copying of the board as an issue, and then there was another issue where we wouldn't divide by floating point, so integer division happened, and yeah, I think this was everything I fixed. I'm not sure I already mentioned this part, but I also assume sometimes we don't find a winning player after a certain number of moves, and we essentially need to make sure that we just say, oh, whoever's ahead now is winning. I played around with a couple of different search depths, so just to show you some outputs. Yeah, here's my debug output. Initially, when I got it working, you see the bottom move is the most promising one, 2-0. I think is also what our alpha beta search suggests. If you rerun it a couple of times, you see not always 2-0 is the winner. And the last two runs, were with different maximum depth. So maximum moves here was basically unlimited. So we managed to do 50,000 moves in 2 minutes, roughly. And if we only do 50 moves, we managed to do 66,000 full playouts. Overall, you see the probabilities are relatively close for the top moves, which is surprising. But I think we get an overall better estimate with higher search depth. This would be a parameter that we could tune. I say if we play 500 moves, this should be fine. I think the last thing we will implement now is add the selection according to UCB1. And we do this by checking. I'm not sure this makes a big difference. Here says it's an optimization. We can try this later too, but I'm not sure this is really a big factor, but you never know. Okay, we now do in this move we get all the legal moves. We play all of the legal moves. This is a bit of a hassle for us. Then we need to calculate if everything is expanded. Then we take this, else we make a random move. With t bigger max depth. What would max depth be? I'm not so sure. I think the rest stays the same. So we don't want to expand too much. Or we want to know how deep we went. Good. I think we can implement this. So now in our loop we need to make sure we generate all the next states, which is something we do in here as well. Basically this. Okay, let's see. So we generate all the next states from the possible moves. If all, And then here we want to append player board string, board to string. We can actually board to string if all if all state in self place for state in next states. Else we do random move. Okay, and here we now need to take this formula, which is the logarithm of the sum of all plays. Ooh, this is really hard to read. Wow, maybe I just look at the formula. Somewhere here. The number of simulations that resulted in a win divided by the node's total number of simulations plus C, exploration parameter, times square root of logarithm of SP. Parent's node's total number of simulation divided by the node's total number of simulation. Okay, let's see if we can get all of these, or as in place, move states. Okay, we need the node's number of simulations that resulted in a win. This node's total number of simulations. So let's see real quick. For state and next states. Equals self place state. Okay. Wins. Self wins state. Okay. And this is for the next node. And then we need the number of plays in the current node. So SI WI SP equals self plays board here I board other player board to string I need to think about this. So wait, oh yeah, I make a move. This will work. The wins of the parent node, no, the simulations of the parent node, and then we should have a formula like this. Wait, or I don't know how to call this. Would be SWI divided by SI plus 1.4 whatever times square root of log S underscore P divided by SI. Something like this. R. Okay. Next states. And then next moves. Let's have an array which stores the move that we take. Next moves, append move. Oh no, we already have this in possible moves. So now we need to next moves equals this. And here we store next moves, append r, move, and I will get the move from here. State, move, in, tip. Sorted next moves -1. This is the move with the highest R, I think. But, okay, this should be the same as this. Log total is the log of some player and S. Ah. Okay, this is interesting. Maybe this is a better way of doing it. I will build an assert that actually assert some self place state for s in next states should be the same as s underscore p value move state, and here we take wins player state divided by place player state, which is for the current node, self c square root log total divided by place player state. Cool. Choice move state. Choice value move state. Okay. Let's see if this what will work. Okay. SP key error. Board other players board to string. This one is the current board for this player. So let's do this. Let me just real quick check that nothing changes in between. Oh. Yeah, this should be. And now it tells me that other player board to string is not there. How can this happen? Print len self place. Let me just see how late in the tree this happens. 20. Na gut. Du bist nicht drin. Board other player board to string. This is exactly not gonna help. Now it's in 40. So let's just, this is not gonna be readable at all. Okay. So 1. It seems though that this one works for now. Let me just comment this out and get back later. And then let's move this insert. And then I don't want to run this for 2 minutes. No, oh god. I should. For 10 seconds. See how much we can get done. So we can see this one was chosen a lot more than this and this, for example. Okay. This looks alright. The only reason is why does this one not work? Okay, let's see. 591, 629. 561. One thing I'm surprised is we get quite unreliable results, like 2, 3 is the worst one here and the best one here, I guess because the sample size is so small. So one thing we can do is we actually let it search a little bit longer. Did I actually fuck this up? Not sure we need this. And I think the rest is the same. One, 3, 1, 3 seems to be such a random choice. 0, 3, no. I will have to tune this a little bit and also read up on how to properly choose the C parameter. And then I think in the next video I will let both engines duke it out against each other. Sorry. 1, 0. Naja. The sum of our next states must be the same as my current. And the exploration gets smaller the higher the C value, because then this term gets bigger. which is not dependent on my current win rate. I think 2-0 is actually the move. 1-0 might work. Na gut. Only 1,600. Good. Where did the 40,000 go that we had before? Plays, wins. Let's try. So if okay. So if wins. Does this help? Okay, last one, then I'm gonna finish this video a bit early. The other one was a bit longer. I will double check a little bit more whether what we just implemented actually makes sense or whether we broke it. We want the highest win rate. Here 2-0 is really bad. I think we need more iterations. It's shocking though that somewhere we lost many thousands. So essentially, I guess doing all this crap is really expensive. Doing move and undo is probably what's slowing us down so much. And I think the algorithm that runs a couple thousand iterations more will be much better than one that favors the better moves, but gets very low sample size compared. Look at this. Seems these two moves are pretty good. So they still find the same moves, but at what cost? How can I make this easier? So we need to find all the next states. Instead of storing the next state, how about I store the current board plus the move. So I can do this. Now I don't need to simulate anymore. Now I can leave this step away. And I can do this, and I can say in pos moves. So I can go move, and then I can do player board toString move. This is still expensive because I'm toStringing the board all the time. In place. Then for move in possible moves. Next. Place for state in next states. Okay. And then we do for state in next states. Do I need? This is gonna be a list. Yeah, and here we need to move. This is P, B. I didn't need this. I don't need this. Yeah, I can unpack the move. Does this just work or will this crash on me? This should be much faster because I don't need this part, which is basically doing a move and undoing the move. And doing the move is expensive. Undoing the move, I'm not sure how I implemented it. I think actually undo is simple because I actually store the arrays. Every time doing the move, I need to copy stuff. Oh, float division by 0. This may have broken a lot of things. State 0 is the player, indeed. Just see. And here we can print games didn't work. Yes. No. Please. Everything has been played 0 times. Because here I need to next states. Next states equals player board string move for move in possible moves. And then this goes away. Board string, board to string. Sorry that I'm not talking much, but I'm really focused. And again, it's a 30-minute episode. Oof. Am I trying? Oh yeah, next states. Yes. Next states. and m equals s minus 1. And we just really have the state now. Get state. Oh, let me fix this at some point. Get state. Okay, cool. This is probably the same, but now it should be much, much, much faster. If we now run this for 30 seconds while I fix the output a bit. Instead of, since calculating the next state is expensive, we just store the current state plus the move that we would take, which is essentially the same as the next state. Okay, 30 seconds with the original, without. Now we have 8 instead of 11,000. 3-3 seems to be popular. Interesting, it comes up with a new thing every time. This is the fun thing about random. Now, under tournament conditions, it would have 60 seconds to think. This is probably the 60 seconds I used to finish up the video. But 1-0, which is a move, this one is also close, so maybe we need to tweak the exploration parameter a little bit so that it actually flattens this curve out a little bit more. And then in the next episode, I want to refactor my game class a little bit. Maybe we can actually make these commands a little bit more professional so that we can actually choose who's playing who. And then we let the two AIs play against each other. But this should be a separate video where I just comment on the moves of the AI. Maybe we can here also plot the principal variation. So we can now see, oh, if we take the move 1-0, what does the AI think is the next best move according to all the nodes that have been expanded. You see 1-0 is very popular. And actually it's good to see that these 3 moves are here. So, okay. See you in the next episode.